Here, a long charged cylinder with linear charge density lambda 1. It's surrounded by another hollow coaxial conducting cylinder with linear charge density minus lambda. Using Gauss law, obtain expression for electric field intensity at a point in the space between cylinders outside the large cylinder. A long cylinder, one section of the long cylinder, it's extending to up and down. Positively charged, charge density lambda 1, linear charge density, surrounded by a cylinder, minus lambda 2 is a linear charge density. Using Gauss law, electric field intensity in the space between the cylinders. So this is one, so second one somewhere in between. We take a point here. We need to imagine a Gaussian cylindrical surface like we have done for the straight, long, infinite rod. This is the Gaussian surface. To find electric field intensity, you need to find the total flux. For finding the total flux, you need phi1, phi2, phi3, phi1 on the top, phi2 on the curved surface, phi3 on the base. This is exactly same as what we have done for the straight long infinite wire using Gauss. For the top surface, the area vector is upward, perpendicular and outward. Since it is positively charged wire, the electric field is radially outward, right on the right side, left on the left side. Base area vector is downward, electric field is still right. Both angles are 90 between E and dA. On the curved surface, E and D are in the same direction. Theta is 0. Now we apply the Gauss law. The distance is taken as R1. Flux is equal to 1 by epsilon times of charge enclosed. Flux will divide into 3, phi1 plus phi2 plus phi3. When charge enclosed, if you take the length of the cylinder as L, 1 meter has charge lambda 1, that's called linear charge density lambda 1. If the cylinder is of length L, the charge enclosed will be lambda times of L1. As already we discussed, phi1, phi2 both are 0 because E and D are 90 degree. So this becomes only phi2 is 1 by E times of charge enclosed. The markings surface 1, surface 2, and surface 3. Now flux is integral EDA cos theta, here theta is 0. Charge enclosed will be 1 meter is lambda 1, so L meters will be lambda 1 L by epsilon. E will go outside. Integral dA will be curved surface area of the cylinder, 2 pi R1 into L. Now from that E you can calculate as LL get cancelled. So lambda 1 by 2 pi ER. So whatever length you take doesn't matter. The length of the cylinder, Gaussian cylinder, it finally get cancelled. So this is the electric field intensity. Any point between the two cylinders. R1 being the perpendicular distance from the thin cylinder inside to the point. The second point, if you take outside the two, the distance is R2. The process remains exactly same. We have to imagine another Gaussian cylinder around this. The top and bottom angle will be 90 degree. Only the field with the curved surface makes 0 degree with the area vector. So phi 1 plus phi 2 plus phi 3 will be same way, but phi 1, phi 3 will be 0. Only phi 2 will come. Exactly same like this, but Q enclosed will be different. The cylinder what you're taking L length, the inner one enclosed lambda 1 L charge, the outer one enclosed minus lambda 2 L. So the total charge enclosed will be lambda 1 L plus minus lambda 2 L. So substituting for phi 2, integral EDA cos theta, charge enclosed is lambda 1 L for the inner positive cylinder minus lambda 2 L for the outer one. Then E comes out, integral ds again 2 pi r2 here. Then LL get cancelled, 2 pi r2 will go to the other side. So that's a final expression for electric field intensity. Length of the cylinder is L. Second case, Gaussian surface is not drawn. That is to be drawn exactly same way, to be confused. Like same way we can draw another big one, Gaussian cylinder. For this case also, the area vector and electric field will be 90, exactly same as the previous one. Only the charge enclosed and the distance is different. On this surface only, you have both the same direction. Zero degree, 90, 90. This is dA, E,